Okay, so today's topic we will be going ahead with the drift velocity. Now we know that every conductor contains a large number of free electrons, and we know the order is somewhere around 10 to the power 22 number of electrons per cc. And these electrons, they are under continuous random motion. They are moving inside a material, inside a conductor, randomly in all possible direction. The result of that is the net current is zero. Under this condition, we say that the velocity, which is RMS velocity for electron, can be represented as Vrms equals to 3 times kT by m meters per second, which is somewhere into 10 to the power 5 meters per second. It is equal to, this is an average value. Okay, so K is Boltzmann constant, T is the absolute temperature, and M is the mass, which is mass of electron in this case. So there is no net flow of electron under this condition. But when the same conductor is now connected to an external source which produces a field across this conductor, then instead of moving in a random motion, these electrons, they actually show their motion in one particular direction, which is decided by this external battery source. So this external battery source, now it decides the direction. But not only the direction, it takes care for the speed, the velocity also, with which these electrons now they are directed towards one end of the battery terminal. Now we know with a very common part that if we increase this potential, no doubt the speed with which these electron drifts towards one end goes on increasing. This velocity with which the free electron in a conductor get drifted under the influence of external field is called drift velocity. We are repeating. Drift velocity is the average velocity with which the free electrons in a conductor get drifted under the influence of external electric field applied. So let's have some mathematics associated with it. Like, let us say that N, it represents actually number of electrons present in that material per unit volume. This is more important, that N is the number of electrons per unit volume. So suppose if we say that we take certain length of this conductor and we want to find out how much electrons they are present within this rather, if I just draw within this volume of a conductor, we can still find out now. Like, we can say it's a number of electrons in length L, of a conductor can be easily treated as N into volume, because we know N is what? Number of electrons per unit volume. So if we take an arbitrary specimen length L, and if we want to find out number of electrons in that length, we can simply say that it is number of electron multiplied by the volume. And we know volume for any particular substance, we can say that it's a product of cross-sectional area into the length. So what's cross-sectional area? Here we say that this is the cross-sectional area of the specimen which is under discussion. This is the area. Multiplied by length, we will get this volume and we will get number of electrons in that. The moment we get number of electrons within this volume, we can simply say that charge We can simply say that charge in that length, charge in that length L, what it will be? It's as simple as N into Al, which gives us the total number of electrons multiplied by charge of electron. So it simply can be written like the total charge Q in that length will be equal to N into E into A into L. That's what is our first basic importance. Then starts the discussion about drift velocity. So we can simply say that drift velocity, drift velocity, which we represent with a parameter v suffix d, that's a variable, and then that can be easily said that it's the distance covered L divided by time taken to cover that. It's a simple thing. It's a velocity is equal to distance covered divided by time, and we know that second one, the electric current can be taken as I is equal to Q divided by T. Now we get equation of Q from this equation, and the value of T can be derived from this equation number 2, so that we can simply write down Q is equal to N E A L divided by time. We can say that this time can be represented like its length divided by the drift velocity. So we now got the value of current in terms of its charge and the drift velocity, which now we know we can straightway cancel this L with this L, which results in a value like N E A into VD. Just 1 minute. I'll just write it down proper way. It's a V suffix D. This is our basic main equation 3. Now, if we just keep on representing the values in different form, I can simply say that making our drift velocity as a subject, I can write down then Vd is equal to, if I take equation 3, Vd will be represented like current divided by, we can simply say that N into E into A. Then the same equation can also be written like current density J divided by N into E, with a reason that J, which is current density, is a current per unit area. So that is our understanding from the basic current density concept. If we can just put it in other way, we can simply say that this current density J can also be written as sigma into E and then Ne as it is. What's sigma? So it's a charge density. So we know that sigma, which is charge density, that can be taken as a current density divided by the electric field strength. So we can represent the same value of Vd in terms of these two parameters also, which can also be represented like the field intensity E divided by Ne. Now I represent it as rho. This is conductivity. Basically, when we talk about charge density, we are talking about actually the conductivity. So, which is reciprocal of resistivity. So, I can simply say that this resistivity or this conductivity sigma is equal to 1 divided by resistivity. It's 1 divided by resistivity, and we get the another equation. They are all reasons for these steps, which can be also written like applied voltage V This is the applied voltage. Okay, so if we just call applied voltage as a capital V, then V divided by L, V divided by L is a field strength. So V divided by L becomes field length, and then N E into rho as it is. So I can simply say that the reason for this step can be written like field strength is equal to V divided by L. And that's a very common thing, that suppose if we do have the two batteries like this, or the two plates, one side is positive, second side is negative. If we increase voltage between these two plates, naturally the field will become strong. And if we increase the distance between the two plates, the field strength will be reduced. So we can simply find out from this example that the field strength is directly proportional to the potential between these two terminals. You increase the potential between the two terminals, we will get a strong electric field. At the same time, if we increase the distance between the two terminals, or distance between these two plates, we find out that the field, it becomes weak. So field is directly proportional to the applied voltage, but the same field is inversely proportional to the distance of separation between them. We use the same concept here, saying that we can write down this electric field E in terms of volt applied per length. So if you increase the length, no doubt electric field decreases. If you increase the voltage, the electric field will also increase. So to get from this step to this step, we have to go on for this assumption. Most of our numericals, most of our questionings which will appear at the NEET level, they make us understanding or need the understanding of these many variations for the same drift velocity. I hope it's clear to you. If there is any difficulty, come back for doubt. Okay, so hope we are clear about the different styles in which we can represent the drift velocity. Now let's take the another way of expressing drift velocity in terms of acceleration. So no doubt when the electrons, they are directed towards any one particular potential side, they definitely show an acceleration. So the same drift velocity Vd can also be represented like the acceleration of electron into something called tau, and this tau, we say that it is treated as relaxation time. It is relaxation time. What exactly relaxation time is? Nothing but we can say that a time between any two successive collisions, any two successive collisions of any electron. So when an electron is actually directed towards any one particular direction, no doubt there are other electrons also in the race. So every electron moving with some different velocity because of the potential difference, there is always a chance of having a collision. Whatever is the time that spends or that is spent between two successive collision, that is treated or that's called the relaxation time. So we get the value like drift velocity is equal to acceleration into relaxation time. That's the basic definition of velocity. From there, we can simply say that this can also be represented like we can directly write down as minus charge of electron into electric field intensity divided by its mass into tau. The root lies here. We know electric field intensity electric field intensity is equal to force per unit charge. We can easily say that it's an electric field intensity. We can say that it is force experienced per unit charge. So let me represent it with charge E. It's a charge part. So I can simply say that that gives me an equation that force is equal to charge into electric field intensity. And we know that F is equal to ma gives us the value of acceleration as F divided by m. If we substitute the values, we can simply say that E into capital E divided by m. The negative sign here is because we are discussing with electrons. It's always electrons. So negative sign simply indicates that we are working with a negatively charged particle called electron. Now, what's the effect of that? So we can again refer back to our basic equation of current. Basic equation of current. So we are reverting back to the equation which we have discussed here, that current is equal to NEA into VD. And this time we are trying to represent VD in terms of acceleration. So the equation it's like N into E into A into VD, and we substitute the value of VD so that it becomes N into A into E, and then it becomes E capital E divided by M into tau, which is a relaxation time, giving us a very different equation that we can say that it will be in terms of, it's like N into E square into A into E into tau whole divided by M. This equation is important in terms of discussing the dependencies of current in terms of, we can say, the drift velocities. So we can write down the equation in this form, which can be easily again will be replaced by an alternative part if the MCQs needs it. It's like that N E square, and then we are representing this electric field intensity like volt per, it's volt per length into tau, and then m was already there. So we got this equation as another more important equation for MCQ solving, and this one is in continuation. We can easily write down this part. And now here we actually complete all the needed equations for following the MCQs. I hope the things are clear. Still, if there is any difficulty, we will discuss on it.